Hi, I'm Mark Barsamian. In this video, I'll be introducing the indefinite integral. This material is from section 5.1 of the book, more specifically pages 324 to 330, examples 2 and 3 are relevant. The corresponding homework is this collection of exercises from section 5.1. Let's recall some things from previous videos. We discussed the definition of antiderivative to say that a function capital F is an antiderivative of a function little f means simply that little f is the derivative of capital F. In terms of this diagram, if you start with capital F and you find the derivative of that, you get little f. And we discussed a common form of question. Is one given function an antiderivative of another given function? That is, the question is, given a function capital F and a function little f, the question is capital F an antiderivative of little f? Well, we discussed how you answer that question by simply finding capital F prime. And if capital F prime equals little f, then yes, capital F is an antiderivative of little f. If capital F prime is not equal to little f, then capital F is not an antiderivative of little f. So in our previous discussion of antiderivatives, we didn't actually learn how to find any antiderivatives. We just learned what it means to be an antiderivative, and we learned how to test to see if a given function was an antiderivative of some other given function. Also recall from the previous video this diagram illustrating the collection of all antiderivatives of this function little f of x equals x squared. So all of the functions in this dotted region are antiderivatives of this function little f of x equals x squared, because if you take the derivative of any of these functions, you get this function. And this made sense in terms of the graphs of the functions of the form capital F of x plus c. Remember that in this diagram, this orange graph was the graph of y equals x cubed over 3. The blue graph on top is y equals x cubed over 3 plus 2. The teal covered graph on bottom was y equals x cubed over 3 minus 2. The graph down here is little f of x equals x squared. And we discussed how the relationship between these graphs on top and the graph on bottom is that the numbers that are the slopes of the tangent lines on the graph above, the numbers that are the slopes of those lines are the numbers that are the y values on the graph below. And we discussed the fact that all of the graphs in the diagram above have parallel tangent lines. So if you find the numbers that are the slopes of the tangent lines on one of those graphs above, at each x value, that the number that's the slope of that tangent line is going to be the same as the number that's the slope of the tangent line on all those other graphs above. So all of those graphs above will correspond to the same derivative graph down below. We discussed how these observations about the function little f of x equals x squared and its various antiderivatives can be generalized to other functions. And that generalization was this theorem about the collection of antiderivatives of a function. So if some function capital F is known to be an antiderivative of a function little f, then any function of this form, capital F of x plus c, is also an antiderivative of little f. So the collection of all antiderivatives of little f of x is in this dotted region. If you take the derivative of any of these functions, you'll get little f. We ended the previous video with a discussion of particular antiderivative and general antiderivative. The idea is that if you make a choice of an actual number for the capital letter c, then the resulting function is called a particular antiderivative of little f. I see there's a typo here. So for instance, the function capital F equals x cubed over 3 is a particular antiderivative of little f of x equals x squared. And the function capital G of x, which is x cubed over 3 plus 17, is also a particular antiderivative of little f of x. But if capital C has not been chosen, then the function form y equals x cubed over 3 plus capital C is what's called the general antiderivative of little f. Note the use of the word the. Realize that this expression is a function form. There's only one such form, so you use the word the when you talk about the general antiderivative. In this video, we'll discuss indefinite integrals, which are defined as follows. First, we have this symbol. Notice that in that symbol, there's the function little f of x, and it's framed by these symbols. This large sort of S-like thing on the left is actually meant to look a little bit like an S. And on the right side of the little f of x, there's a dx. We'll discuss why this symbol is used in a future video. This symbol is spoken the indefinite integral of little f of x. Now what does it mean? It means the general antiderivative of little f of x. Remember, we've discussed that. The general antiderivative is the antiderivative form, the function form, that has the plus c. So a remark is in order. We know that given one function, capital F of x, that's known to be an antiderivative of a function, little f of x, we know that we can get all other antiderivatives by adding constants to capital F of x. That is, the general antiderivative of little f of x is denoted by writing capital F of x plus capital C, where capital C is a constant that can be any real number. So what that means is really this. If capital F prime equals little f, that is, if capital F is an antiderivative of little f, then the indefinite integral of little f of x is capital F of x plus c. Now some additional terminology, notation. The function little f of x that's inside the integral symbol is called the integrand. And the unknown constant c that's on the outside is called the constant of integration. The indefinite integral can be illustrated by the diagrams below. So suppose that you have a function capital F that is known to be an antiderivative of a function little f. Then the indefinite integral of little f is this general antiderivative, capital F of x plus c. And again, note the wording. The wording of indefinite integral says the indefinite integral, whereas the wording when you talk about antiderivatives is you say an antiderivative. That's because there are many antiderivatives, but there's only one indefinite integral. So in today's video, we'll learn rules for finding indefinite integrals. First, though, we'll simply revisit some of our examples of antiderivatives from previous videos, and we'll rewrite the results using the new terminology and notation of indefinite integrals. Remember that in the videos for homeworks 68 and 69, we found that capital F of x equals x cubed over 3 and capital G of x equals x cubed over 3 plus 17 were both antiderivatives of this function, little f of x equals x squared. They are particular antiderivatives of little f of x equals x squared. Now using integral notation and terminology, we would write the following. The indefinite integral of x squared is x cubed over 3 plus c. That is, the general antiderivative of x squared is x cubed over 3 plus capital C. So the process is If you take this function form and find its derivative, you get little x squared. And if you take that function little x squared and you find its indefinite integral, you get back to the function form. In the video for homework 68, we found that for all real numbers n not equal to -1, capital F of x equals x raised to the n plus 1 over n plus 1 is an antiderivative of little f of x equals x to the n. Using integral notation and terminology, we write this following integral equation, which will be our first indefinite integral rule. It's called the power rule for indefinite integrals. That's the rule. Notice that the qualification n is not equal to -1 is crucial to that rule. So that is, when n is not equal to -1, the general antiderivative of x to the n is this expression, x raised to the n plus 1 over n plus 1 plus capital C. So in a diagram, that would be illustrated this way. This symbol, the integral symbol, equals this function form, which is the general antiderivative of this function, where n is not equal to -1. If you take this function form and you find its derivative, you get x to the n. If you take x to the n with n not equal to -1 and find its indefinite integral, you get back to that function form. In another example in the video for homework 68, we found that this function, capital F of x equals x ln of x minus x, is an antiderivative of little f of x equals ln of x. Well, using integral notation and terminology, we would write the following indefinite integral rule corresponding to that. It's called the ln of x rule for indefinite integrals. It says the indefinite integral of ln of x equals this function form, x ln of x minus x plus c. That is, the general antiderivative of the function ln of x is this function form, x ln of x minus x plus capital C. And in a diagram, that would be illustrated this way. If you start with that function form and you find its derivative, the result is ln of x. Or if you start with that function ln of x and you find its indefinite integral, the result is that function form. In another example from the video for homework 68, we found that this function, little g of x, is an antiderivative of itself. A simpler result would be the following. The function e to the x is an antiderivative of itself. Using integral notation, we would have this indefinite integral rule. I would call it the e to the x rule for indefinite integrals. The indefinite integral of e to the x is e to the x plus c. So let's think about that in a diagram. Take that function form, e to the x plus c, find its derivative, and you get e to the x. If you start with e to the x and you find its indefinite integral, you get back to that function form. Now I want to turn to a very interesting and sort of difficult topic, finding the indefinite integral of 1 over x. If we tried to find this indefinite integral using the power rule, we would find this. Well, we would write our function as a power function. Then we would try to find its indefinite integral. We would find that the indefinite integral does not exist. But remember, the power rule does not apply to the case of a power function with n equals 1. So that whole batch of stuff that we just did is invalid. So the question then is, how should we find the integral? How should we find the indefinite integral of 1 over x? Well, here's the rule. It's called the 1 over x rule for indefinite integrals. It says the indefinite integral of 1 over x is ln of absolute value of x plus capital C. In this equation is valid for all x not equal to 0. In terms of a diagram, if we take that function form, ln of absolute value of x plus capital C, and we find its derivative, we get 1 over x. And if we start with 1 over x and we find its indefinite integral, we get that function form, ln of absolute value of x plus c. Now that rule just came out of nowhere, so we should think about how we can understand it or find it believable. So to understand this integral rule, we'll need to understand the corresponding derivative relationship. That is, if f of x equals ln of absolute value of x, then f prime of x equals 1 over x. That's the derivative relationship that corresponds to this integral equation. If we take the derivative of this, we get that. In single equation form, we'd say d dx of ln of absolute value of x equals 1 over x. But where did that derivative relationship come from? Well, to understand that derivative relationship, we should examine the graphs of y equals ln of absolute value of x and y equals 1 over x. To start, let's remember what the graph of ln of x looks like and why. Remember that the graph of y equals ln of x is obtained from the graph of y equals e to the x by interchanging all the x, y values. So this graph of y equals e to the x has some famous points. To get the corresponding points on the graph of y equals ln of x, we interchange those x, y values. Notice that the domain of y equals ln of x is the set of all x greater than 0. That is the interval from 0 to infinity. Now think about the graph of y equals ln of absolute value of x. It looks like this. We've got these same famous points on the right side of the graph, but we also have the mirror image graph on the left side. The domain of this graph is the set of all x not equal to 0. Now consider the graphs of y equals ln of absolute value of x and y equals 1 over x. We'll put ln of absolute value of x on top, and we'll call it f of x. And we'll put the graph of y equals 1 over x on bottom, and it's playing the role of f prime of x. Now, remember the relationship between the graph of a function and the graph of its derivative. You start by imagining tangent lines drawn on the graph of little f of x, and you find their slope. And those numbers that are the slopes of those tangent lines on the graph of f are the same as the numbers that are the y values on the graph of f prime. Well, we see that the right sides of these graphs do correspond nicely in that way. But what about the left sides? Well, the left sides are just the mirror images. So we see that the numbers that are the slopes of the lines tangent to the graph of little f of x equal the numbers that are the y values on the graph of f prime of x. So it's believable that if little f of x equals ln of absolute value of x, then little f prime of x is 1 over x. So therefore, this corresponding indefinite integral rule makes sense. The indefinite integral of 1 over x equals ln of absolute value of x plus capital C. That's true for all x not equal to 0. Now, recall the constant multiple rule for derivatives. If f of x is a function and a is a real number, then the derivative of a times f of x equals a times the derivative of f of x. The corresponding rule for integrals is as follows. If f of x is a function and a is a real number, then the integral of a f of x equals a times the integral of f of x. This rule seems obvious enough, but we'll see that there is a bit of subtlety in the issue of the constant of integration, the plus c. That subtlety will be best discussed in an example. So here's a summary of the indefinite integral rules that we've discussed in this video. The power rule, the 1 over x rule, the e to the x rule, the ln of x rule, and the constant multiple rule. The rest of this video will spend using those 5 rules to find a bunch of indefinite integrals. Question A. Find the indefinite integral of x squared. Well, the first thing to notice is that the integrand, the function inside, is a power function with n equals 2. So we should use the power rule with n equals 2. The power rule says you can replace that thing, the integral expression that has a power function as an integrand, you can replace that expression with this expression. So we copy down one of these on the right-hand side, as long as n is not equal to -1. So on the right-hand side, we write x raised to the 2 plus 1 over 2 plus 1 plus capital C. Notice the left side of the equal sign has the integral expression. The right side of the equal sign does not have the integration symbol, does not have the dx, but it has the plus c, and it has this arithmetic going on with the new exponent and with the new denominator. Now we simplify. Notice that corresponds to our earlier examples from previous videos. We found that x cubed over 3 plus capital C was the general antiderivative of x squared. Let's go on. Indefinite integral of x to the 8. Well, here we have a power function with n equals 8. So how does that work? Remember, the power rule says you replace this integral expression with this expression. Notice that the plus c goes on right away. As soon as the integration symbol goes away, the plus c gets put on. Let's go on. The integral of x. Well, here we need to note that x is a power function with n equals 1. The result is the indefinite integral is x squared over 2 plus c. And again, note that the constant of integration goes on as soon as the integration symbol goes away, in that very step right there. Question D, the indefinite integral of 1 dx. Well, here we need to observe that 1 is also a power function. The result is that the indefinite integral is x plus c. Notice that in the original integral, there is no x, but an x shows up when you use the power rule. So that x wasn't there before. So you don't do 1 to the 0 plus 1, you do x to the 0 plus 1. On the right side of the power rule is the symbol x raised to the n plus 1. So even in a situation like this, where your integral does not have an x, you create an x to use the power rule. Now this makes sense. The derivative of x plus c is 1. So that means the indefinite integral of 1 is x plus c. Question E, indefinite integral of 1 over x to the 8th. Well, here we need to put this integrand in power function form. Now we can find the integral. The result is the indefinite integral is minus 1 over 7x to the 7th plus c. But notice that we did this in a couple of steps. We converted the integrand to power function form so that we could use the power rule, and we ended up with a result in power function form. But it's nice to leave the final answer in positive exponent form. Let's go on. Question 5, indefinite integral of 5x to the 8th. Well, here we'll use the constant multiple rule. Now here we have a strange thing. When we move the constant 5 outside the integral using the constant multiple rule, we end up having the 5 in front of these parentheses, where we're going to put the result of doing that indefinite integral of x to the 8th. When we do the indefinite integral of x to the 8th, we end up with this expression that has a plus c inside those parentheses. So officially, that 5 gets distributed as shown. The 5 gets distributed to both those places. So we end up with this result that has a 5c being added to it. But think about this. The number c can be any real number. So this is a function form. But if c can be any real number, then 5c can be any real number. So this expression, 5c, has the capability of being any real number. Well, we can just change the name of that. So I can simply replace this plus 5c with this plus d. These are the same function form, even though they look different. They represent the same general antiderivative. That's what I meant earlier when I said the constant multiple rule seems obvious enough, but there's a bit of subtlety in the issue of the constant of integration. So the idea is that when you use this rule, you have to think a little bit about what the constant of integration really is saying, what it represents. Officially, the result has a constant of integration written this way, but that same meaning can be conveyed by just simply writing the constant of integration that way. Now, question G, the integral of 5 over x to the 8th. Let's start by writing the integrand in power function form. Now our indefinite integral goes as follows. The result is the indefinite integral is minus 5 over 7x to the 7th plus capital D. So again, we replace this constant of integration, 5c, with just a simpler looking one, d. 5c could be any real number, so d can be any real number. Let's go on. Indefinite integral of 5 over x. Well, here you have to be careful. In the previous example, we rewrote the integrand in power function form. 5 over x to the 8th is equal to 5 times x to the minus 8. In this example, we do not want to rewrite the integrand. We do not want to write 5 over x equals 5 times x to the minus 1. That's power function form. The reason is we can't use the power rule when n equals -1. It is far more helpful to simply separate the constant 5 from the function. So 5 times 1 over x is actually a form that we can use. So the integral goes like this. The result is that the indefinite integral is this function form, 5 ln of absolute value of x plus capital D. That capital D could be any letter that I want. I could use the capital K. I could actually use capital C. Doesn't matter. The key thing is, when you end up with a constant of integration of that form, 5c, where c can be any real number, you realize that 5c could be any real number. So I could replace 5c with just d, or any number that I want. Let's go on. Indefinite integral of 5 squared of x. Well, here we should rewrite the integrand. So the integrand 5 squared of x can be written as 5 times x to the 1/2. That's power function form. That's the form we want for finding the indefinite integral. The result is the indefinite integral is 10x to the 3/2 over 3 plus d. Notice all the steps that had to be done very carefully. First of all, use the power rule, and we ended up with this messy expression for the exponent, 1/2 plus 1, and also for the denominator, 1/2 plus 1. We had to be careful with the arithmetic. 1/2 plus 1 equals 3/2. And then we had to note that dividing by 3/2 is the same as multiplying by 2/3. Then we had to distribute the 5 to both these places. But as before, when you end up with a constant of integration that's plus 5c, well, since c can be any real number, 5c can be any real number. So we can just replace the 5c with d. So the result is this expression. Lots of arithmetic, lots of steps. Only 2 steps involving indefinite integral rules. The constant multiple rule, the power rule. 4 steps of simplifying. All of these steps were simplifying. Let's go on. The indefinite integral of 5e to the x. The indefinite integral of 5e to the x is 5e to the x plus d. Now, this one is a little interesting. Here it helps to note that this integrand can actually be written as a constant times a power function. So the indefinite integral goes as follows. The result is that the indefinite integral is 5x plus c. Now this corresponds to the derivative equation. The corresponding derivative equation is that the derivative of 5x plus c equals 5. Notice that I simply replaced the constant of integration, 5c, with just c. This is kind of sneaky, but it's actually valid. Since in this expression, c can be any real number, that means that 5c can be any real number. So this function form represents 5x plus a symbol that represents any real number. This function form is 5x plus a symbol that represents any real number. So again, what I said earlier about the constant multiple rule being simple enough, but having some subtlety about the additive constant of integration, we see that keeps coming up. Our last example, we'll do the indefinite integral of 5 ln of x. The result is that indefinite integral equals 5x ln of x minus 5x plus d. Here I've just simply replaced the additive constant plus 5c with the additive constant plus d. Again, since capital C could be any real number, 5c can be any real number. So I can replace it with some other letter which represents any real number. That's the end of that extended example, and that's the end of the video. Thank you.